In this follow along, we're going to examine manganese dioxide as an oxidant. Now, this one has a special place in the world of oxidation because of the manganese used, which has an affinity for the pi system. So the way that manganese dioxide you'll see most commonly used in synthesis is as a selective oxidizer for allylic alcohols. You can see that right here. So manganese dioxide looks like this. And you don't often see, a mechanism used, but I'm going to propose one. And I'm going to use similar mechanistic motif that we've seen in PCC and Jones oxidation. Now, the key difference here is that the selective oxidation is going to oxidize the allylic alcohol, which is primary, and leave the non-allylic primary alcohol alone. So if you look at the product, you see that there's a selective oxidation. So this is kind of cool from a chemoselective perspective. You have two alcohols, both of which are primary and could be oxidized, but only one of them gets oxidized selectively. So this is kind of a neat reaction. Now, in future chapters, we're going to see that transition metals, and if any of you guys have taken inorganic chemistry, you'll know that the d orbitals of many transition metals are brought in or attracted and coordinated to p orbitals, right? We've seen pi stacking when we discussed Diels-Alder reactions, and this is a very attractive force. Sometimes it's written as a pi bond, and what you'll see is that they draw it right in the middle. They say, here's a transition metal, and they use dotted lines to say that the transition metal is attracted to the p orbitals of that alkene. And this is what brings things close together. Oftentimes, this is the type of thing that lowers the transition state energy and allows a reaction to maybe catalytically move forward. So remember that atoms come together. Atoms are made up of electrons, and electron clouds repel. How do you get two things to come together and actually bond? Well, you've got to get the attractive forces there and lower that energy barrier to get them to bond. So transition metals often can serve this role of bringing things, using it to be attracted to something, bringing it in close so that the chemistry can occur. So I'm going to redraw this carbon 1, 2, 3, 4, 5. Carbon 1, 2, 3, 4, 5 with the alcohol. So now notice that the manganese is attracted to the oxygen, but it's also attracted to the pi system of that nearby double bond. So when we consider the reaction of manganese dioxide, it has been sort of drawn in by the p orbital of the alkene, and that's from a proximity standpoint why it's so reactive with the allylic oxygen and not drawn as closely to the other non-allylically related oxygen at 5. We could consider similar chemistry here where this is more of a in-up 1-2 addition type thing. There's potentially proton transfers, as we mentioned in previous oxidizing examples. This is just, one of the ways that we could potentially think about this reaction. And then in solution, perhaps another one of the manganese that got attacked. Who knows? I'm not quite sure what the conjugate base would be. But you could imagine the E2 happening because it's, again, the E2 where the electrons form the new carbon-oxygen bond and the manganese gets reduced, just like we saw with the chromium. Except this time, manganese is the metal that's reduced. It's still attracted to the pi system in all of these cases. But we see a very similar trend, right? It's still a very similar flow of electrons. The only difference here is that the manganese was brought in close as it was attracted to the p orbitals of the alkene and thus selectively oxidizes the nearby alcohol at the allylic position. This is what gets us to the final product of the aldehyde. 1, 2, 3, 4, 5, the alcohol. And there you go.